So this was the first page.
Yeah.
Exactly. The good egg.
Okay, so I'm gonna go to the page that I was talking about. Did you see this page I was
No.
summarizing?
No, we did not see it.
No, we see it.
No. Okay, well, what I was saying that I assume that the brain is a computational engine and that it processes information. And the brain, like any other computing device, would have to follow and do things the way the information wants to be processed. So information either can be put together or can be separated from each other. So brain processes information associatively and distributively. And any computing device that deals with information would have to do that because the information itself invariantly is a quantitative stuff. And as far as what we know from neurosciences, that the cortex, the neural structure, is a distributed one, which fits very well with the description, the way information want to be fed, because it can distribute the information over the neurons, and when it needs it, it collects it associatively. Now, we learn about the brain from computers. Initially, computers were just simple machines with a central memory, but they have evolved also to a point where it has a distributed structure. So I assume that whether it's a biological computing device or an electronic, over many years, because of the survival and the need to get faster, have eventually evolved into a distributed structure. This distributed structure, to make decisions, it has to model scenarios, evaluate them before we make decisions. These four aspects are the assumptions that I have to come up with this scientific thinking framework. Do you see that I have changed the picture?
Yeah.
Yeah.
Okay.
You have this multiple circles and the concept.
Yes. Okay. So the circles are on top of each other. At the center of the circles are the distributed and associative nature of information. Okay. So I have a plus and minus, but the picture on the right is basically telling you what I mean. That information, as I said before, you can either put the details and pieces together to make concepts and or you break the concept down to its pieces. This two-way processing is the basis of this framework. Again, the associative processing, distributed, and then its cyclical and iterative nature is important because, as you know, that the nature itself, the matter itself, also follows this cycle. You either after the Big Bang, either the pieces have gone away, but later those pieces have become larger masses, and those larger masses then at some point again broke down to pieces. So this two-way cycle is what I see happening in the matter and the information itself. What has our brain done? It had to adjust to this and process the information in this dual way. So the cognitive processes whether it is deductive reasoning, inductive reasoning, abductive reasoning, they can be described in terms of these associative and distributive way of processing the information. Now here I talk about device independent computational processes, whether we have electronic computers or biological computers. We learn about the biological computers by experimenting on the electronic computing. And I think that's the advantage that we have in this age. Both devices in the quantum computers as well, they just process quantifiable information through computation. There are device independent processes. No matter which device you do the computation, that two-way and the associative and distributive way of processing it is a fixed thing because of the invariant nature of information. There are also device dependent processes. Biological computers have neurons and electronic computers have circuits, and they share some features. Today, both computers and the brains, they all have distributed architectures, as far as I know. Information comes in and it scatters to the neurons, and then when it needs it, it retrieves them through the neural pathways. Okay. Now, I have to talk about modeling and simulation as it relates here, because it is through the modeling and simulation work that I have come up with this framework. So basically, if you use, whether you are a scientist or a student learning science through modeling and simulation, the modeling and simulations have deductive and inductive pedagogies involved. It allows you, again, to process the information following this thing here on the right, okay? Because you either put a model together based on details, come up with a concept or the model, and you test it, whether that's an airplane or a car or something, or a climate model. If it doesn't work, then you break it down to its pieces and you update them and you put them together. So this two-way cycle goes on and on. That's how science has progressed, and that's how we have learned, and that's how the brain learns. As far as educational implications of this approach, I have trained more than 1,200 teachers using modeling and simulations, and their data on students show remarkable progress. Like in Rochester City School District, the math scores went up by 40%, and science scores went up about 30%. And we have also done some retrieval experiments, how students learn and retrieve some information at a later time, using the same framework, assuming that the brain operates like this. Again, if we follow those retrieval practices in the classroom, we see also student score go up at least by one grade. If the control group compared to control group, the target group does much better. So I basically claim that scientific thinking is nothing more than how brain processes information in an inductive and a deductive way. But the key here is the iterative and cyclical nature. We have tendencies as humans, maybe to process information in one way or another. And I've seen, among friends and families, that is the case. Usually, husband wants to simplify things all the time, and the wife wants to go into the details. So they have different tendencies, but one has to do it both ways. Okay, so that takes some practice, and if we can teach that to people and students, I think they will have a great skill to learn and to do conceptual change. Basically, I think this was the last slide. I don't know if I've
You
gone
just
over
mentioned that
my
you
time.
have to, you had taught about more than 1,000 students. Can you let us know which school is this and what kind of a
So
program it is?
I train more than 1,200 teachers. These
Teachers.
teachers, yes. So if you multiply these teachers, each teacher teaching 100 students a year, that's a big number of students.
Oh,
Yes. So, at least,
and these are in your university, or is I mean, it's a commercial operation or it's a university
yeah. So
program?
I am a professor at the State University of New York,
New York.
at Brockport, which is near Rochester. So I've done my work over there, and teachers have come from Rochester, Syracuse, Albany, New York City, about 40 school districts. So it was a regional project, and I have testified before the U.S. Congress actually about the success of this project. So that's why I had to dig in to see why the students are doing well, which is what led me, thinking
So it's a
about.
one-time project, not a degree program.
No, we had a degree program, but this experiment was on high school and middle school students.
Uh-huh.
Yes, yes.
Excellent.
So I am currently on leave from the university. I work at a nonprofit company in Boston, the Institute for Future Intelligence. We have tools, simulation and modeling tools, and then enhanced with AI. We're the tools are in-house tools. They are designed by the company, and we're doing some exciting things at this point. But my work with the university is just in the SUNY system.
That's great.
And it has been supported by the National Science Foundation. So for the last 20. But now, what happens at NSF?
What is the name of the program in Boston that you are associated with? I live in Boston.
You do? Oh,
Yeah.
okay. Well, I'm currently in Boston, right, in Natick.
Oh, you're Natick? Oh, I'm in Lexington. Yeah, close to Cambridge, Boston. Yeah.
The Institute for Future Intelligence.
It's in Natick? Where is
Yes.
it located? Okay. I'll look it up. Yeah.
Yeah, look it up.
Yes, thank you.
The Institute for Teaching Intelligence?
No, future.
Future.
Oh.
Yeah. Tomorrow.
It's an ambitious name. But I am a senior vice president and a chief scientist. I write grants. Currently, I've written a few grants, but we haven't heard anything yet.
I shall send you the detailed descriptions of our Oxford project, a very similar effort to promoting system thinking to youngsters. But that was another topic. Anyway, any more questions for Osman? Lauren?
What was one or two of the biggest challenges in this program?
Well, challenges. Of course, you have to reach out to teachers and students. That's a big challenge.
Marketing.
Getting teachers to commit to the program.
Right.
It's a big challenge, and administrators don't help at all. When I got the project, I went to the district, talked to the superintendent. Nothing. They didn't do anything. So I said, I better just go reach out to teachers and just ignore the administrators. And I gave ownership to teachers, like they felt like they are part of the project, they own. So I think that was important. Other challenges, I don't know. I think processing the data that we collected to make sense out of it was a challenge. I had to learn things that I didn't know about educational research and cognitive sciences.
How long was the program last? I mean, one run.
Well, I had multiple projects. So the first one was from 2003 to 2010, and then another one started, all the way to 2022. The last project I had was to teach them retrieval practices, how to bring back what they have learned initially. And there is a book, I don't know if you've seen it. It's called Make It Stick.
I mean, how long is a teacher needs to be staying with you for one semester or 1 month or multiple years, or what it looks like?
You mean the involvement of teachers?
How long
Yeah.
does it take you to teach the teachers? Yeah.
Oh, okay. So I had that 3-tier program. Voluntary, okay. Of course, there were incentives. If they gone through introductory and intermediate and an expert level, there would have been 3 different summers, okay? They would have been in the program. The way it works is the return rate is like if you start with 100 people, the next level you get 50, and then the last level you get 25. So it goes, health. We had, we ended up with a good number of expert teachers who became instructors for the program. So at least three years of involvement.
I see.
Are the lectures online or the lecture notes online?
The curriculum modules are online. Or we're online. I don't know whether I don't know the link to it because I have Ahman and Lee from the university at this point. But it was being downloaded at an annual rate like 40,000 downloads every year all over the world. To run those, to utilize them, you had to have some tools. They're not expensive. One of them is called interactive physics. The other called agent sheets. And then there are some web-based free tools. I think one of them is from Colorado. It's called PHET, PHET. And I just heard that NSF has canceled their project.
Hmm.
Gerald, you have a question?
Yes. This is about the process of teaching. You assume that there are certain processes in those people who are learning. For example, they can use deductive reasoning. At the same time, you are teaching them deductive reasoning. So I assume that in the beginning, they have only a primitive form of deductive reasoning, and then you teach them the finer details. I wonder about the relation. Do students have to have an initial deductive reasoning process, or can they do without?
Yeah, for students or teachers, we don't assume actually any back prerequisites. Yes. So, and that's the good thing about it. That down to middle school level, we were also training some elementary teachers, but I haven't collected any data from them as far as student achievement scores.
Okay, thank you.
You
No more
noted,
question?
yeah.
Yep.
You
Go
noted
ahead. Go ahead, Jerry.
Okay. You noted the relationship between associative and distributed relationships. Do you also consider commutative relationships?
Wouldn't it not be also based on those two?
That's the question. Should
Yes,
it be or
yes,
not
yes,
be?
yes. Well, many of the cognitive reasonings, they're using this associative and distributed, but there are higher level cognitive processes, as you said, which also is based on them. We did not single out, the commutative relationships and how they fare out, but I'm saying that it should include them. The analogical, when you do an analogy, you compare information, or when you look for causal relationships, I think they are a little at a higher level. It involves more than just a simple associative and distributed processing on some piece of information.
And the notion that information is invariant is sort of fundamental to the
Yes.
logic involved?
Yes, the information wants to be treated in only two ways. Information is quantifiable, which means it comes in pieces. That was also the assumption that Alan Turing made when he tried to mimic human brain. He said that the brain is working on information, and information is coming in pieces. So we can assume the same thing with the computers. I think it was easy to see it with computers because they add and subtract, multiply, whatever. but whether that reflects, whether that manifests itself in some high-level cognitive thinking, it wasn't clear until this age. I mean, artificial intelligence about even until 6-7 years ago, it wasn't going anywhere because it was trying to compute all the possible scenarios in a situation to make a decision. And you had to have a nuclear power plant dedicated to a supercomputer, which was running all these AI computation. It was very expensive. When they started to see how humans are making decisions based on little information, we cut corners. When we make decisions, we don't have all the data, and we don't consume a lot of energy. The brain is consume as very little energy. So it was those cutting corners and making decisions in a practical way is, I think, what led to AI in the last couple years to speed up. Yes, all of this is based on information being quantifiable, and then it either is put together to make bigger pieces, or you break bigger pieces down to small pieces. And I am a physicist, and I can see that the matter itself behaves the same way. So I try to make some meaning out of it. Why is information acting like the matter itself? And the sensory information, whether it's coming through radiation or heat or touching or whatever, I think the information is reflecting because it reflects from the matter. It acts like the matter. I don't know. I cannot prove that, but it's information is everything is information. Basically, that's what I'm saying. The matter itself is information. And it's quantifiable. Because it's quantifiable, it's acts computationally. But we might end up discover other forms of information. I'm not sure, but I think there may be.
Rem?
Yes, so
Rem?
I think Dr. Ramesh wants to say something.
Rem, you have a question? Okay, it's frozen.
Maybe we can get together in Boston and talk more about this.
Okay, Jerry, your turn to do your presentation.
Would you like to go next, Jason, or?
I mean, either way is fine, but I'm curious about your
All right.
what you're going to say as well.
Yeah. Okay, so let me share screens. Where is screen share? Here it is.
At the bottom.
Jason, my computer seems to freeze up. Did any of you have any issues in the last couple of minutes? No?
No, you just froze when I was trying to ask you. Do you have a question? And your video
I was
stopped.
talking, nothing happened. No, I was asking a question and it froze. So that's okay. We can get back to it later. Sorry about that. Something funky about my computer is freezing. Okay.
You looked very intelligent when frozen, though.
Uh-oh.